cells. Generally, that's the structure of a neural cell. We have many types of neurons. Also, the neural cell is called the neuron. So the general structure, we have what we are calling cell body, we have axon, and we have that axon at the terminals is ramified, okay, as you see, to give what we are calling axon terminals. Now, also we have dendrites, as you see, which are connected to the cell bodies. Now, these neurons, generally, if you have a motor neuron, that motor neuron is generating action potential at this part of a neuron, which is the junction between the cell body and axon, and that junction is called axon hillock. We will see why we are generating only in that part the action potentials. Now, in your nervous system, there are a lot of what we are calling supportive cells, which are helping these neurons, and they have a lot of functions in the nervous system, helping these neurons to keep the media around these neurons clean media. Okay, so we have many functions for these supportive cells. We will not go through these functions, but generally, I think you know some of these. They are providing nutrients for the neural cells, for example, ready for the consume of neural cells. Some others, they are working like phagocytic cells, so they are keeping that media around the neurons very clean without pathogens and so on. So by that phagocytic activity of these supportive cells, in addition, they are keeping very low concentration of potassium in that media. Why we are needing very low concentration for potassium? Actually, to have optimal activity for the cell membranes of the neurons that we are having. In addition, as you see here, we have one type of cells which are wrapping around the neurons, the axons of some neurons, okay, and these are secreting or forming high amounts of myelin. You know what the myelin is? It's a sphingolipid forming like a sheet of many layers around the neurons, okay, around the axons of neurons, which are, these cells are called the Schwann cells. As you see here, they have nucleus, and giving this appearance for the neurons. And these types of neurons, they are called myelinated neurons. But you are finding some neurons that are not myelinated, so they are not having these Schwann cells wrapping around to form these myelin sheaths around parts of the neuron. But you have to realize that we have small parts of the axons here, which are called nodes of Frambier, and these small parts are not covered with these myelin sheaths. So we have interruption here, forming what we are calling nodes of Frambier. We will see the importance of these nodes of Frambier in getting propagation of action potentials that is generated at this part of a neuron, which is called the axon hillock, between the cell body and the axon, and then spreading along the axons toward the terminals. So what happens at the terminals? What we have in these terminals, we have neurotransmitters. Once we have the action potential reaching these terminals, that action potential causing release of neurotransmitters from the terminal. So this is of a neural cell is to generate action potentials. We'll see how we are generating these action potentials at the axon hillock here, and we are getting propagation of that action potential toward the terminals. And at the terminal, these action potentials are causing release of neurotransmitters into a small space here. That terminal is connected with another cell body of neurons. Okay, we'll see that later on, and we'll see what we are calling that connection between the terminals of the first neuron and the cell body or the membrane of the second neuron, which are forming an anatomical structure which is called synapse. That's the synapse, which is between the terminals of the first neuron and the membrane of the second neuron. We will see what happens at the terminal. So we said we have a lot of supportive cells. They have different names, as you see, but one of them, they are called Schwann cells, which are wrapping around the axons, forming that myelin sheath in myelinated neurons. Okay.
دكتور
تفضلي.
مطلوب منا نحفظ الأجزاء تبعت النيورون.
You will know them with time يا بنتي. انتم ما ليش بتضلكم تسالوني بدي احفظ وما بدي احفظ؟ اوكي؟ هذا السؤال ما بنسال. مع الوقت هاي تيرمز لازم تعرفوها. عرفتي؟ اوكي.
تمام دكتور.
I will not ask you about what are the astrocytes, what are the oligodendrocytes, for example, but you have to know what's the axon. You have to know what's the cell body. You have to know what's the dendritic, what is the terminals, okay, to differentiate and to understand the lecture. Without these terms, you cannot understand lecture. Anyway, so we said we have what we are calling myelinated neurons and unmyelinated neurons. تفضلي.
بس بدي أغلبك بس فيك تعمل البرزنتيشن فول سكرين.
It is
لا على باوربوينت تعملها إنه فول سكرين على الباوربوينت.
صرت تعمل فول سكرين للبرزنتيشن، يعني تخليها أكبر صورة لأنه الأسماء صغيرة صراحة مش مبين.
ايش عمل از برزنتيشن؟
هي تحت عندك في 4 أجزاء.
ريكوردد. انا ما بقدر ابلش في المشاكل التكنيكال يا بنتي. عنده الواحد محاضره تحضير تيرم، تحضير بطريقه انكم تفهموها وبالاخر تسالون عن تكنيكال بروبلم. انا ما بقدر اتابع كل التكنيكال بروبلمز، ولا بعرف كيف الطريقه ان اعمل مثلا اعملها بس ان تيمز. بتصير ريكوردد وبتصلكم ريكوردد، شو بدكم اكثر من هيك؟ Anyway, so we will talk about how we are having the action potentials. We assume that we already have an action potential generated at this part of a neuron, which is between the cell body and axon, which is called axon hillock. So what happens to that action potential? As you see, if you are looking in series for that action potential, at that moment it is at this position. After a while at that position, after a while at that position, and so on. So in series, it is propagating toward the terminals of the neurons. That type of neuron here, it is unmyelinated neurons. We haven't myelin sheaths which are covering the axon. So what happens at this part to get the propagation of action potentials along axons toward the terminals? إذا بتتذكروا لما حكينا في currents بتصير. So once you have action potential, for example, at the axon hillock at the beginning, okay? Once you have that action potential here, so what happens here? You have the channels open, sodium channels, then potassium channels, and so on. Now, what happens to the activity of the membrane here? Becoming what? Positive inside, as you see, inside the membrane of the axon. negative outside the membrane of the axon. And because of that situation, as you see here, positive, here negative, positive inside, negative outside, and here also positive inside, negative outside. We are creating currents between the regions where we have action potentials which are already developed inside with the region which is still polarized. Polarized meaning it is still at resting state at the inside. Also, we have these currents at the outside, but the most important are currents which we have them in the inside axon here of neuron. By these currents, what happens to the neural region here? We are getting depolarization. The depolarization reaching threshold. Once you have reached threshold, you are developing the whole action potential as you see here. After a while, action potential at that point. After a while, action potential at that point, and so on. Okay. So if you are looking in series, the action potential is propagating along that axon toward the terminals in a continuous way. And because of that, we are calling this type of conduction, the action potential, as continuous conduction. Okay, so that's the continuous conduction that we are having it. We have it in unmyelinated neurons. What happens in myelinated neurons? We have different story actually. As you see, some parts of the axons are covered with myelin sheaths, so they are not generating any action potential. So what happens? The currents that we are having developed, they are developing between the nodes. So once you have action potential here, you have currents inside to depolarize the membrane at this node of Ranvier. By depolarization of that membrane, we are reaching the threshold, generating an potential here is also causing depolarization of the membrane at the next node, and so on. So if you are looking in series for what happens, it's like the action potential is jumping from one node to another node to another node until reaching the terminal, jumping or salting. Okay, so this type of conduction in myelinated neurons is called saltatory conduction. That's the continuous in unmyelinated, while in myelinated, as you see, calling it as saltatory conduction. That's the saltatory conduction that we have it. So if you will be asked about what type of conduction that we are having in unmyelinated, it is continuous. If you would if you have been asked about what type of conduction in myelinated, it is saltatory conduction along these axons. Now, the principle of generation is the same. Okay, as you see, action potential here causing depolarization of the membrane here. By the depolarization, you have reached threshold, you are generating action potential at that level, and so on. Another current causing depolarization of the next, and so on. Which of these two types of conductions is faster? The in myelinated, because we are skipping big parts actually of the axon as you see. So by skipping these big parts, we are getting much faster conduction for the action potentials along the axons. So in myelinated axons, we have faster conduction than unmyelinated axon. The type of conduction again in myelinated is saltatory, and in unmyelinated is continuous conduction. Now, assuming you have two different types of axons, one with a small diameter and one with bigger diameter. Which of these, which of these axons you can have higher or faster propagation of action potentials in smaller diameter fibers or bigger diameter fibers?
The bigger.
Bigger. Why bigger? That's true. Why?
كوندكتنس أكتر
بيكون معزز أكتر للتيار.
حساسية أكثر كان زي
Why bigger?
ريزيستنس أقل
لأنه بيعمل نيرف
Exactly. As you know, we have current inside, mainly inside that axon. Okay? Once you have these currents, now sodium ions, for example, are moving from one part to another or so something like that. Positively charged particles are moving, mainly sodium, okay, inside. Now, where you have resistance to that ionic currents in small fibers, where you have it higher, in small fibers or in bigger fibers? Smaller fibers. Once you have in smaller fibers higher resistance for these ionic currents, that means the velocity of conduction along these unmyelinated axons, okay, will be, once you have higher resistance, the velocity will be less actually. Once you have lower resistance, so the lower resistance for these currents are in bigger fibers, okay? Once you have lower resistance, you will get much faster transmission of action potentials along these unmyelinated axons. So the velocity of conduction along axons can vary also. In addition to that, they can vary according to myelination. They can vary also according to the diameter of the axon. If you have smaller diameter axons, you will get lower velocity of conduction. In bigger diameter axons, you will get higher velocity of conductions. Okay? وضحت? Okay, so again, you have seen how we are generating these currents between the region where we have action potentials and the polarized regions of the nose of Ramsey and myelinated, or the Nirabi region in unmyelinated. And by these currents, we are depolarizing this part of the membrane, getting action potential, then depolarizing again the next part and getting action potential. Now, are we developing currents behind also between that region where you have action potential with the region behind action potential? Are we developing?
in all direction yes
No.
We are developing actually, but these currents are very small currents. They are called subthreshold currents. They cannot generate a new action potential at that part which is behind of the membrane, which is behind the region where we have action potential. Why we cannot regenerate a new action potential at that part? Because that region of the membrane is still in refractory period. Once it is still in refractory period, here you are at the overshoot, okay? But behind that, so that region has passed the overshot. Now it is in repolarization. In repolarization, it is in during the relative refractory period. So once it is during the relative refractory period, these small currents cannot cause that membrane to regenerate a new action potential. So that's the importance of refractory period. It's ensuring propagation of action potentials only in one direction, from the region where they have been generated toward the other terminals of the neuron. So if we have them generated at the axon height, look, they are propagating only toward terminals. Question is, are we generating action potentials only at the axon high look?
No.
Huh?
لا دكتور.
Okay, we have also other types of neural cells, as you see here. They have what we are calling receptors in our body, and these receptors are sensing changes. For example, changes in temperature, changes in we have, for example, pain receptors, touch receptors, and at these receptors. Then the action potentials is transmitted toward the nervous system, okay? Not toward the cell body, as you see here of these cells. These types of sensory neurons, the first sensory neurons, it is having like this shape. We have cell body. The axon is in the form of T axon, T, like T letter, okay? So we are generating action potentials at that part of the terminals. These action potentials are transmitted toward the central nervous system, but they are continuing with an axon to have another terminals where we have the second terminals here are synapsing with a second neuron. Okay? So in that way, we have the first sensory neuron is working. We are generating action potentials at the terminals of one part of the axon, which is in the form of T. Then we have transmitted the effect toward the other part of the terminals where we are getting release of neurotransmitters here in the other part. Okay. Now, we have seen that we can generate action potentials by neural cells. Now, what happens at the terminals, actually, between the terminals and the membrane of the second neuron?
دكتور
تفضلي.
بالسنسوري بتمر الاي بي بمر بالشو اسمه بالسيل بودي
No, no, it is transmitted directly along the axons toward the second neuron.
يعني بيجي من التيرمينال يلي فيه ريسبتورز للتيرمينال يعني بيكون فيها هي
To the terminals, the second terminals, that's true. Okay? Okay. Now, at the terminals, what happens actually? Okay, so what we have in these terminals? We have vesicles, and these vesicles are having what? Neurotransmitters. So the purpose of having this action potential is to reach terminals, and by reaching that terminals to cause release of neurotransmitters from these vesicles. How we are getting that? Simply, once we have action potential reaching terminals, at the terminals here we have calcium channels. Okay? So what happens to these calcium channels?
Open.
Once we have action potential reaching these channels, it is open. Sorry. By opening of calcium channels, what you are getting?
بيكون from جوا.
From where to where?
From outside to inside.
From outside toward inside the terminals. Once you have increased calcium concentration inside terminals, you are causing more vesicles to dock with the membrane, okay, of the terminal here, fuse with the membrane, and by docking and fusion, you are getting exocytosis of the content. So the content of these vesicles now is released into that small space between the membrane of the terminals and now the membrane of the second neuron. The whole structure is called synapse. Okay, so in that way we have at that level transmitted the electrical activity that happens here in the first neuron toward the second neuron by activation of channels that we are having. Okay. Now we'll talk about these channels, what happens to these channels. We have receptors linked to these channels, and by activation of these receptors, we are activating these channels. So the whole structure that we are having here, it is called synapse. One question before, what type of calcium channels we have here at the terminals? Are they are voltage gated. Exactly. They are sensing the action potential which has reached these terminals. Once we have the action potential reach these terminals, activating these calcium channels. So these are voltage gated channels. Now, what happens actually to get more vesicles docking with the membrane and to get more release of the neurotransmitter of in that synaptic cleft? What happens? What happens to the vesicles by calcium?
Activation the phagocytosis or
Okay.
exocytosis.
Imagine that these vesicles are polarized vesicles, so they have negative charges, for example, over the surface. And the membrane is negatively charged inside, as example. So what happens during resting state? Here we have repulsion between the presynaptic membrane, that part of the membrane of the terminal which is synapsing with the membrane of the second neuron is called presynaptic membrane. We have repulsion, electrostatic forces causing repulsion. Now, once you have increased calcium concentration, you have neutralized a lot of charges that we are having. By neutralization of charges, you are getting attraction actually between the vesicles and the presynaptic membrane. Once you have that attraction, you are getting fusion of the two membranes and then exocytosis. So in that way, we have the mechanism of exocytosis. You remember when we have talked about vesicular transport is also regulated. This is one of the ways of regulation. By increasing calcium concentration inside, we can cause more secretion of the neurotransmitter out of the terminals here. Also the same thing, a lot of secretory cells are working in the same way. Okay. By increasing calcium concentration inside, we are getting the release of their content. Could be a hormone, could be another ligand or something like that. Okay. Now, so the whole structure, what we have, it is called synapse. We said we have terminals. The membrane, which is belonging to the first neuron, it is called presynaptic membrane. Now, the membrane, which is belonging to the second neuron, it is called postsynaptic membrane. What we have over postsynaptic membranes? We must have receptors first for the neurotransmitter. That's it. We have channels also. Okay. We have channels also. What type of channels we have here? Are they chemical gated or voltage gated? Chemical gated because the ligand has bind to its receptor, for example, and cause these channels to open. Now, what happens if we have the types of channels are sodium channels? What we will get at the postsynaptic membrane?
Excitation.
Depolarization.
Are we getting action potentials?
No,
In
yes.
first step, yes.
No, we are not getting action potential. We are getting only small depolarization. Small depolarization. Each channel may cause small depolarization. That channel causing small depolarization. That channel causing more small depolarization, and so on. Okay, so we are developing potentials over the second neuron, over the membrane of the second neurons, which are called postsynaptic membrane potentials. What types of potentials that we are developing? Are
Subject
they
pressure.
depolarizing? Are they hyperpolarizing waves?
depolarizing.
Default.
Depends. Depends on what? On the type of channels that have been
channel.
activated. If you have activated sodium channels, what you are getting?
Depolarization.
You have if you have activated potassium channels, what you are getting?
Refall.
Hyperpolarization. So as a response of the postsynaptic membrane, you can get either depolarization, but not reaching threshold again, or hyperpolarizations, okay? And these potentials, which have been developed at the postsynaptic membranes, are called postsynaptic membrane potentials, okay? Explaining what happens more, as you see. We have needed calcium. How we have activated these calcium channels? They are what type of channels again?
Voltage.
Voltage gain.
Channels. We are getting entry of calcium toward the terminals, the increase in calcium concentration causing more vesicles to dock, causing fusion, and causing the release of their content into that small space. That small space, by the way, it is called synaptic cleft. Okay? So we have presynaptic membrane, we have postsynaptic membrane, which is belonging to the second neuron, and we have very small space between the two membranes, which is called synaptic cleft. The postsynaptic membrane is having what? Receptors. Exactly, receptors. These receptors are linked to channels. Okay. So what types of channels we have at the postsynaptic membranes? They are chemical gated channels. Now, if you have activated sodium channels, you are getting small depolarizations, but not action potentials. If you have activated potassium channels, you are getting what? Hyperpolarization. So these types of channels, you know them, they are called chemical gated channels. You know these types of channels. Okay, so this is uh, showing you a summary that we have a receptor linked to a channel, and by having ligand binding to this receptor can cause activation of the channel. Now, are we having only one synapse between two neurons? Are you having only one terminal, for example? No.
No.
As you see in the picture, you can have many terminals synapsing with the cell body of the second neuron. Okay. You can have terminals from many sources, from different, okay, neurons, presynaptic neurons synapsing with one neuron, and we can have that situation. So the cell body of the second neuron actually is, we have a lot of synaptic structures at that level, and through these synaptic structures we have many terminals synapsing with that cell body. Could be from one source, could be from many sources that are synapsing with one cell body. This part of a neuron is called the axon hilum. You remember that. Okay. Again, here is summarizing this part. So we have channels, we have receptors, we have binding of the ligand, which is the neurotransmitter to its receptors, causing what? Causing activation of channels, and these channels are chemical gated channels. Now, are all these synapses terminals? Okay, are all of them causing activation of sodium channels?
No.
No.
Are all of them causing activation of potassium channels?
No.
أو
No.
Okay. Now, you can find some terminals which can generate what we are calling excitatory postsynaptic potential, not action potential yet, excitatory potential, which are characterized as excitatory presynaptic neurons. You can have some terminals which are causing hyperpolarization, as you see, and these hyperpolarizations, they are called inhibitory postsynaptic potential. Why we are calling them inhibitory? Why we are calling these are excitatory? The excitatory,
ما عم بيعمل action potential.
excitatory have brought the resting potential closer to the threshold, as you see. Okay, but we haven't reached the threshold. The inhibitory have caused the change the membrane potential to a more negative potential, which is far now from the threshold. Okay, so what happens to these potentials actually? Once we have a potential generated here at that membrane, it is migrating along the cell body. Okay, so we have migration of these potentials, positive and negative and so on. But the propagation is different from the propagation of action potential. If you remember, if you have an action potential, you will have the same amplitude all over the axon for the generation of action potential. Same. For example, up you are reaching the plus 30 and so on. All over the axon you are getting that. Here you have getting small depolarization, for example, from minus 85 to minus 80. Okay? If we have propagation at a distance, the minus that wave will not be also at that point, for example, will not be minus 80. The tip here will not be minus, will be maybe minus 82, 83, and so on. But what happens between these potentials? These potentials are summing with each other. What we mean by summing? So you have one excitatory potential here, minus 80, for example, meeting another one minus 80. Now you are getting a higher amplitude, maybe minus 85. Okay, sorry, 75. You are summing. You are summing also the excitatory potentials with inhibitory potentials. For example, if you have here at the minus 90, that part is at the minus 80, for example. They are canceling each other, returning back to the minus 85, for example, as potential, and so on. So we have a process of summation for these waves. Now, at the axon hillock here, where we are generating action potentials in that neuron, if the sum of all these potentials at that axon hillock, after their migration, summing with each other and so on, reaching the threshold, we are getting generation of action potential at the axon hillock. If the sum of all these potentials not reaching the threshold, we are not getting generation of action potential at the axon hillock. So that part of a neuron is taking the decision now to generate a new action potential or not to generate an action potential. We have processing for all these potentials, inhibitory, excitatory, and so on. If the sum of all potentials reaching the threshold at the axon hillock, we are getting generation of action potentials. If the sum is not reaching the threshold at the axon hillock, we are not generating a new action potential at that part. Don't forget, we are getting summation of both types of potential, the excitatory with excitatory, excitatory with inhibitory, inhibitory with inhibitory, and so on. Okay? So the sum of all, after the integration of all these potentials, we have integration at that part of the axon, which is called axon halo, to get decision to generate or not generate action potentials. So these are the types of potential that we can get. So more hyper or hyperpolarizations, which are called inhibitory postsynaptic potentials, or depolarizations, as you see, but not action potentials again, which are called excitatory postsynaptic potentials. Now, for the purpose of understanding of the events that we are having, for example, if one stimulus, okay, causing that small depolarization, the second stimulus is coming, causing that small depolarization. Now, what happens if we have two stimuli, one after another, okay, coming, and still the first, or we have depolarization by the first one, for example, and the second one, okay, from the second stimulus is coming, we are still at that depolarization. So you are getting more depolarization, and so on. So it depends on the frequency of these action potentials that are coming from the first neurons, we can get summation process. For the purpose of understanding, actually, we are going to this figure. As you see here, you have to say one source which can cause excitatory postsynaptic potentials over the second neuron. Now, one stimulus from the first neuron here is causing small depolarization, as you see. But if you have many action potentials coming from the first one after another, so after ending each action potential, you are getting a new action potential at the first neuron here. What are the effects over the postsynaptic membrane? The first has caused depolarization. The second stimulus coming, causing more depolarization. Third stimulus coming, causing more depolarization. And so on. And we have reached the threshold. So what happens at the second neuron now? It can generate an action potential. This is called temporal summation. Temporal. Over time, we can have only one source, one presynaptic source, that can cause more depolarization if you have the first neuron is generating high frequency of action potential one after another to cause activation or generation of action potential at the second neuron. That's the temporal summation. While the second type of summation is called the spatial summation. As you see, you have two neurons, two presynaptic neurons, A and B, synapsing with a third neuron, which is the C neuron, for example. If you have only one stimulus from the A, you are getting small depolarization. If you have only one stimulus from the B, also you are getting that small depolarization. Now, what happens if we have the A and B, the stimuli coming at the same time to the cell body of the second neuron? You are getting a higher depolarization by the effect of the two. We have summed the effect from the first neuron with the effect from the second neuron to get a higher depolarization, reaching threshold. Once you have reached threshold, the third neuron here now, the postsynaptic neuron, is generating the action potential. So this type of summation is called the spatial summation, which is different from the temporal summation. You have to figure out one thing, okay, as you see the duration of action potential, okay, from this point to that point, okay, is much less than the duration of the potential. The potentials are having longer time, as you see, than the duration of the whole action potential. But the amplitude has changes in voltage, and the action potential is much higher than the amplitude that the changes in voltage, or the amplitude in the changes in voltage is much higher in the action potential than in these graded potentials, or some they are calling them sub threshold potentials, and so on. واضحة؟
دكتور
دكتور عادي
ايش حكيت اخر شيء؟
ايش؟
اخر اشي حكيته تبع الوقت عادي تعيده.
Okay, the time, you know, over x-axis is the time, milliseconds, شايفينه؟ The time for the action potential, the whole action potential is much less than the time for the excitatory potentials. The time for excitatory potentials is longer than the time for the whole action potential. وضحت؟
دكتور كملت حكيت في اشي بس بيكون اكثر من الثاني، ايش هو؟ غير عن الوقت.
amplitude of voltage. انت تطلع على الاكشن بوتنشال لاي فولتج بصل بلس 30 اوم، صح ولا لا؟ اما الثاني لاي وين بصل؟ بس 5 ملي فولت changes من الماينس 70 to minus 75 to minus 65 for example, as this according to this example. As amplitude which is the changes in the y-axis. وضحت؟ Okay, I think we have few slides left. I will talk about these slides next time actually. So this is only to show you the summation process. You can have, don't forget, we can have summation between excitatory with excitatory to reach the threshold. You can have also summation between excitatory with inhibitory. They are canceling each other, so you are not reaching the threshold in this case. Now, what happens if you have activated chloride channel? This is a question for the next time answer. We said by activation of sodium channels, you are getting excitatory potentials. By activation of potassium channels, you are getting inhibitory postsynaptic potentials. Now, what happens by activation of chloride channels?
بتعادل الصوديوم يعني.
Actually, yes, that's what happens. If you have activated more chloride channels, you are preventing any depolarization that can happen by activation of sodium channels. And because of that, we have some neurotransmitters which are activating at the level of the central nervous system, okay, which are activating chloride channels. They are characterized as inhibitory, okay, inhibitory for the generation of action potential. They are inhibiting or preventing generation of action potential. Anything that prevents generation of action potential, it is called inhibitor, okay? So these receptors are characterized as inhibitory receptors, the receptors that are activating chloride channels. Any questions?